Hello everyone, this is Chandan Purohit from Satvik Softech. So in this video, I'll be discussing some problems, some programs which appear in the VTU syllabus of 2018. So this is the syllabus copy which I have with me. The syllabus hasn't changed much in the past 15 years. Things don't change so easily in India, so we should not expect many things to change here. But there are a few nice programs here which help us to really appreciate computer science and mathematics alike. So this problem is the problem which I am going to solve today is the one which is shown here. So there are others here, Taylor series, bubble sort. We'll be solving a few of those, but the one which I am concentrating in today's video is the program. Develop a program to find the square root of a given number n and execute for all possible inputs with appropriate messages. So you are not supposed to use the library function square root. Okay. So we also have a problem statement here which asks us to implement a binary search. So this is the sixth program in part A. Introduce one-dimensional array manipulation and implement a binary search. So the first version of our program will actually use binary search to implement a square to find the square root of a given number. So we'll be solving two programs in a single with a single problem statement. Okay, so let us begin this. So the question is, you need to find the square root of a number. So we can solve this in many ways. The first way can be to treat this as a search problem, because you are trying to search for a solution. So the square root of 5 is definitely going to be somewhere between 2 and 3, right? So the square root of 4 is 2. The square root of 10 will be 3 and between 3 and 4, right? So how can we come up with these kind of guesses? Because of the fact that the square root of a number is always less than or equal to half of that number. Okay, so if I take up, say, 10, so half of 10 is 5, so it is definitely going to be less than or equal to 5, right? Similarly here, so the square root of 5 is between 2 and 3. Okay, so we can go on reducing the search space by half every time until we reach a number which is very close to the square root. Okay, the reason why I am saying close, you'll understand it when we start implementing. Okay, so let us try this out. We will have a binary search. So binary search. So how does binary search work? So suppose you want to find the square root of 5. My first guess is going to be 3. Or you can take it as 3 or 2. Okay, depending on what you take. The next approximations will be dependent on what you take here. So if the first approximation is 3, okay, then what I do is I check for 3 square, which is 9, which is greater than 5, right? So that means I need to now search between 0 and 2. Okay, so my next guess will be somewhere between 0 and 2. Okay, between 0 and 3. So between 0 and 3, that is going to be 1.5, right? So if I square 1.5, definitely I will not reach 5. So the next guess is going to be 3 plus 1.5 by 2, so that is 4.5 by 2, so that is going to be 2.25. so if you observe here, we are getting close, 2.25. if you observe here, we are getting close to the actual square root of 5, right? So we can go on doing like this to finally reach a number which is close to the square root of 5. Okay, so how does this work? To do this, we need to have variables. So binary search, there are many good examples of binary search. You will find it online. So let me just solve this problem. So binary search takes the number, okay, that you are trying to find the square root of. So it is going to take another number which is the low part, another number which is the high part, right? So it's going to return an int. So actually we should not take an int, we need to take a double, because the square root should not be an int, it should be a double. The square root can be a double, so we'll take this as double. Similarly, the low and high will also be doubles. Okay. So we need to have some kind of the error here. So how close should a number be to the actual square root so that we can stop our search? The reason why we need to do this kind of a we need to put a bound on the error is because we are using doubles. So you can't directly compare two floating point numbers too. So you can't, if I have say 2.5, okay, so it is always a bad idea to compare two floating point numbers like this. So what happens here is that computers cannot accurately represent floating point numbers. So if you compare them like this, chances are that you will not get a right answer. So it is always a bad practice to compare floating point numbers directly like this. So you should always compare them by calculating by putting some kind of a bound. So in mathematics it is called, the bound is generally specified using a special variable called epsilon. The same thing will be using here. So the epsilon, this is going to be our bound. So I'll say 0.0001. This will be my bound. Okay. So actually it is better to make this epsilon as a constant and make it global, because we are not going to modify this throughout our program. So I'll make it as a constant. Okay. So when this binary search gets called, so first I'll write a main function, int main. This will be printf square root of, so I'll take a number here, double number equals say 5. So let's the best one is 2. We'll take 5 because it's a little bit big. So square root of percentage left is percentage left. Okay. So this will be num and binary search. So the number is 5 and low is 0. So what will be high? We'll keep it as 5. Okay. What is this? There are no errors here. Fine. So how does this work now? Once I pass, this is the number, this is the square whose square root is expected. So I start from 0 to 5. Okay, so my entire search page is now from 0 to 5. So I can have any number between 0 and 5 as the square root, right? So instead of taking this as 5, it is better to take this as num, so that we can use this for testing. Oops. So now that I have my template set up, let me implement the binary search. So a non-recursive solution will be something like this: while I need a variable here to keep track of the square roots which are generated. Double current root. Okay, double current root equals, will not have any equals here. Okay, current root equals low plus high divided by 2. So that is my current root. While the current root into the current root, that is the square of the current root. So this will give me the square of this root. Okay, we will make use of the mathematics library function to calculate this square. So we need to include hash include math.h. So math.h has a function called power, POW. So we'll make use of that to just ease our work. So raise the current root to power of 2. This will be my current approximation. Double current approx equals. Okay, so while my current approximation minus the number, so we'll have an absolute subtraction. That will be a better one. Abs will help us. So it is just going to give me a positive number always. Whether current approximation is greater than number or less than number, that is immaterial. I just want how far is the current approximation from the expected number. Okay, so absolute value, while the absolute value is greater than epsilon, as long as this is the case, what should we do? We should go on getting the new approximations. So I'll just copy this line, we don't need a double here. So change the low and high. Okay, so if the current approximation is if the current approximation, so this is my current route. Okay, so I need to check here if my current approximation, if the current approximation is greater than the number, just comment this out. So if my current approximation is greater than the expected number, that means I need to that means my square root is between the low and my current approximation. So I need to change the high. My high will now be my current root. Okay, else if my current approximation is less than my number, if it is less than my number, that means I need to change my low. So low will be my current root. Okay, so we go on changing like this. We can actually just go ahead and take these two lines inside the while loop. We will need these inside the while loop also. We don't need these doubles. This condition I just put it inside the while loop. Just remove these because anyways we are doing this inside the loop. So we get into an infinite loop where every time I just calculate the current root and then get my current approximation, and then I check here if it becomes less than epsilon, my current approximation is less than the epsilon, then I just break out. Okay, otherwise I just keep on getting new approximations. I guess this should work. So once I encounter a square root whose square is closer to this number based on my epsilon that I have chosen here, then I just get out of the loop and I print out the result. So I just return my current root. Okay, so I guess this should work. Let me try this out. program has been written. So just compile it here. gcc square root dot c. Okay, so there is an undefined reference to the power function, and it is giving some warnings related to printf. So to get rid of those warnings, we need to include the stdio.h, and to get rid of the undefined power function error, so we need to add the mathematics library while compiling. So implicit declaration of the function apps. Okay, I think there is an apps function. Let me just check it out. Okay, so apps function is present within the stdlib.h. So just include that also here. Hash include stdlib.h. We should never ignore warnings. So now this is a clean compilation. If you run, so it is saying 2.1875. I guess this is right. Let me just check this out. So in my Python console, if I say math dot square root of 5, so that is 2.23606. 2.23606. The margin is quite big. Margin is quite big, should not have been this bigger. So where is the output? Okay, so let me just run this once again. 2.1875. so let us check this out. How is it calculating? We need to get it closer. We need to certainly get it closer. So let us just check whether it is working properly. We'll just print out the current root every time we come here, just to verify how it is working. So this will be my %lf \n current root. Actually we'll also go ahead and print out the highs and lows. Low, this is again %lf, and high is also %lf. The root, so just print out all these values so that we can trace out how it is working. And just compile this once again. So it started from 0, so it first started from 0 and 5. 2.5 is the first case, then because the square of 2.5 is greater than 5, so the next case it is taking between 0 and 2.5, so that is 1.25. so the square of 1.25 is less than the actual square expected. So now the low becomes low plus high by 2, and that is the square root itself. The high is still 2.5, and then the half of this is calculated, right? So half of this is 1.875. Square root of 1.875 is again less than 5. The square of 1.875 is less than 5. So again low changes. Low is now 1.875 and high is 2.5, and the next square root is this. So what happens here is 2.1875. so if you look at the square of 2.1875, again if you look at the square of 2.1875 square, that is 4.78515,625. so if I say 5 minus 2.1875 raised to 2, so that is going to be 0.214. So there is a mistake here, I guess, some mistake here. So what is that mistake? So if the current approximation minus the number, so absolute value of current approximation minus the number is less than epsilon. So how is it breaking out? I guess we need to print out the current approximation also. I'll just add a printf here so that this will give us more details about why it is not working. Just print out the current approximation. Okay. So here we have it, the current approximation, that is the square is 6.25, now then it is 1.56, and then it is 3.515, then it is 4.78515. okay, if that minus my number is less than epsilon. So what is epsilon? Epsilon is 0.0001. So I guess I need to check out what is this. Okay, so I guess we had some problem here. So the problem here is the abs function. What is the abs function? What is the purpose of the abs function that we are using here? So the abs function computes the absolute value of an integer. However, the number which we are having here, this is not an integer. So if you try to compute the abs of this, there is going to be a truncation, and because of the truncation, so the program is going to exit abruptly. So we need a better way to compute the abs. So I need to compute the absolute value of a number irrespective of whether it is an integer or not. I think we should be able to get more details about this. let us check out the cabs function. This is the absolute value of a complex number, so we don't want a complex number. So let us check this out. So Google is always our best friend. Absolute value of double in C. There is already a question here. So use fabs instead of abs, obviously. So we need to make use of fab. So instead of abs, we'll use of fabs. And we will actually remove this because we already know what is the problem. As you can see here, the value which we get now, it is much better. It is 2.236061. okay, so the actual square root, I'll just print out the actual square root so that we can compare our result. The square root is this. I'll just add another statement here, print the actual square root. Actual square root of so the square root function which comes with the maths.h, it comes with the math library. It gives us this answer 2.236068, whereas the one which we wrote is giving 2.236061. so that is quite good. We can improve the accuracy by decreasing this error. So if you go ahead and do it like this, it is going to give us much more accurate answers. See, so accuracy is almost the same, but how many iterations is it taking? If we look at this, we can go ahead and also print out how many iterations it takes. Instead of printing all these things, I'll add a variable here to keep track of how many iterations it is taking. So lab experiments should always be treated as experiments. You need to experiment with these. So I'll just keep a count here. Better, instead of giving it as I'll make it as iterations so that I know what this variable really means. So every time inside the loop I am going to increment iterations plus plus. So every time I get into the loop, I increment these iterations. I'll put it before the end of the loop, because every time I enter the loop I need to consider that as one iteration. So once I have iterations, I'll printf %d, so iterations, so this is my iterations variable. Okay, so if you observe, this is going to tell us how many iterations my program is going to take. So it is taking 27 iterations to arrive at this answer. If I want a little bit less accurate answer, it may take a few iterations less, so it is taking 20 iterations, but now the accuracy has gone down a little bit, so it is 2.236066. okay, if I increase this number, if I increase the number that I am giving here, so instead of giving 5 is a very small number, so if I give a big number, say 150 or something like that, you will observe that the iterations are going to increase. So taking 28 iterations, which is still good. So if I make this as 1500, so now it is taking 32. So from 150 to 1500, that is a huge leap, but still the number of iterations that it is taking, it hasn't increased by a huge amount. So that is the power of binary search. A very simple problem, but it is able to solve a very simple algorithm, but it is able to give us good accuracy within less iterations. So now iterations is just 35, whereas my number is 15,000. okay, so in my next video I'll come up with another implementation of the binary search, making use of recursion, and then we'll come up with a better method called the Newton's method, which is a very famous method to calculate the square root of a number, and we'll compare that with binary search and see how Newton's method outperforms binary search. okay, hope you enjoyed this video. We'll again